Alright, let's sketch the function f of x is equal to 2x minus 2 times x minus 4 squared times x plus 1 with attention to degree, terms, intercepts, order, local and absolute, minimum, maximum, and domain and range. Okay, so let's start by looking at, first of all, the leading term of this function, right? So we can notice that there's x to the power 1 here. If you square this, if you expand this portion, the highest degree would be x squared times x to the power 1. So normally you want to do this as 2 times x to the power 1 times x squared times x to the power 1. And this is going to give you a leading term of 2x to the power 4. Okay, so this tells us a few things, right? So you can think about your leading term as ax to the power n, right? Your degree here, n is equal to 4. Okay, so your degree is 4. This tells us that our maximum number of turns, which are the points of extrema, the maximum number of turns here should be n minus 1, so it should be equal to 3, right? This also tells a here is greater than 0, right? So if a is greater than 0, this tells us that it's positive. And because the degree here is an even number, right? This is a positive even degree function. So this is a positive even degree function. This tells us that we'll have similar n behaviors because all even degree functions have the same n behaviors, and the n behaviors would be in quadrants 1 and quadrants 2 because it's a positive even degree function. Okay, so now that we know that, right, we have our n behaviors, let's find our intercepts. Well, it's really straightforward to find your x-intercepts here, right, because we know that factored form is in the form of f of x is equal to a x minus r, x minus s, x minus t, and so forth, right? But in this case, the roots, or x-intercepts, are in the form of r and 0, s and 0, and t and 0. Okay, so we can find our x-intercepts by letting f of x equals 0, and if you do that, your roots here would be 2 times x minus 2 times x minus 4 squared times x plus 1 is equal to 0. So therefore, x can be equal to 2, 4, and negative 1. Okay, so those are your x-intercepts. Now, after you find your x-intercepts, you also want to figure out the behavior of the x-intercepts, right? So let's look at, so these are our roots, right? And then this is, the behavior of the x-intercept is characterized by the order or the power on each factor. And we're going to look at the behavior. Okay, so roots 2 and 0, 4 and 0, and negative 1 and 0. At 2 and 0, we can notice that, right, it's a power of 1, so this tells us that the order is 1. At 4 and 0, order is 2. At negative 1 and 0, for this factor, the order is also going to be 1. Okay. At 2 and 0, behavior, it should pass through it. So it passes through. At 4 and 0, it should be concave to that point. At negative 1 and 0, it should also just pass through that point. Okay. Now that we have all that information down, we can also figure out a y-intercept to complement our sketch. I'll just do that here in different colors so we can visibly notice it from the rest. The y-intercept, I'm going to let x equal 0, so I'm doing f of 0 here. And if I plug this in, 2 times 0 minus 2 is negative 2. 0 minus 4 is negative 4 squared. 0 plus 1 is 1. And you basically get negative 4 times 16, so it's like negative 64. So the y-intercept is 0 and negative 64. Good? So now that you have your x-intercept, your y-intercept, your order, the number of turns you expect, let's create a sketch here. Okay, so remember that this is a quartic function, right? Similar n behaviors. Let's make a nicer sketch than that. Over graph. Okay, I'm not going to draw this to scale. Don't really have the space for that, but, right? We just want to plot some of the key points here. Okay, so let's plot our intercepts first. Okay, so let's say that this is 2 and 4, and let's do, this is negative 1. Okay, so this is 2 and 0. This is 4 and 0. This is negative 1 and 0. Okay, and we also have a y-intercept. Let's say this is 0 and negative 64. Right? And let's draw our trace. Let's do it in blue here. We notice that it should end off in quadrants 2 and end off in quadrant 1. So one of your sketches, your curves, are going to do this. So one of your curves are going to do this because the end behavior is the second quadrant, and it's going to pass through -1, and it's going to cross the y-intercept. Okay, so once again, guys, sketch, right? I would definitely recommend doing this in pencil. It's kind of hard to do this in pen, right? And then what's going to happen here is it's going to loop back up, right? It's going to pass through the 2, but then we know that at 4 it's going to be concave to this point. Right? It's going to loop back up towards one of the end behaviors is going to be in the first quadrant, right? So this could be a potential curve. Sketch. Okay, so this is our sketch. You can see that there's similar end behaviors, positive infinity, right? And now we can actually see the presence of a turn here, there's a turn here, and there's a turn here, okay, at the x-intercept. Alright, let me just think it'd be easier if I just do that. Okay, so there's 3 turns here. That's consistent with what we have algebraically, right? The only thing we need to actually kind of figure out is this point here, this x value of the turn, and its equivalent y value of the turn. Now, because this is an even degree function, we're going to have local maximum minimum, but more importantly, we're going to have an absolute maximum minimum. And let's actually mention that here, right? If we look at our domain, the domain is going to be consistent for all polynomials. X belongs to the set of all real numbers. There is no restriction on the domain, but the range here is going to be restricted because there is going to be an absolute minimum point, right? There is an absolute minimum at 0 and -64. Because of the fact that the leading coefficient is positive, you will have an absolute minimum. Now you can notice here, because there is an absolute minimum, all other points will be greater or equal to -64. So this actually restricts our range. Okay, so keep that in mind. We also need to figure out this maximum here. We can see that there is another minimum point. There's a local minimum at 4 and 0. Right? But we still need to figure out this maximum point. So to find this maximum point, what we need to do is we need to find the midpoint, right? So the x value of the turn here is 2 plus 4 divided by 2, which is 6 over 2, which is 3. And then you just do f of 3. Okay, so you do 2 times 3 minus 2, 3 minus 4 squared, 3 plus 1, and then you get 2 times 1 times -3 squared times 4, which is like 9 times 4 is 36, times 2 is 72. Okay, so f of 3 is 72. So this point here, it doesn't, I know the sketch doesn't look too good, but you get 3 and 72 here. It's not too consistent with the sketch, right? So this is it's gonna be a much more higher peak, right? Once again, just a sketch, guys. So it's good to kind of just figure these points out algebraically, right? So we should also have a local maximum at 3 and 72. Okay, so that's our local and absolute minimum maximum. We have our end behaviors, we have our domain range. Basically, this is our completed sketch. Alright, let's sketch a possible graph for the following function. F of x is equal to negative x minus 4, x minus 1 times x plus 5. So this is a function, a polynomial function in factored form. And just off the bat, you can notice here that there's a negative on the outside. So we want to look at factor form as f of x is equal to a, x minus r, x minus s, x minus t. And you can notice that because there are 3 x values to the power of 1, if you multiply them together, right, you should get an x cubed term. Then whatever a is going to be for the leading term is going to be a x cubed. Okay, so this is your leading term. Well, we can notice here that the leading term here is -1, so your leading term here should be, like the leading coefficient, sorry, is -1 because you have a -1 here. So the leading term here should be negative x cubed. Okay, so it tells us that this is a negative odd degree function. Okay, this is an negative odd degree function. Degree is 3, so the degree here is 3, so n is equal to 3. The turns should be n minus 1, right? The maximum number of terms that you'd find in a function would be n minus 1, and the terms are basically points of extrema, right? So because it's n minus 1, then we know that the maximum number of terms you should have here is 2, right? You can have a minimum and maximum, or maximum and minimum. Now, because we know that this is a negative odd degree function, this tells us something about our end behavior, right? We know that odd degree functions, if they're positive, it's quadrants 1 and 3. If they're negative, the end behavior should be in quadrants 2 and quadrants 4. Okay? Having said this, now we want to look at our intercepts. Well, specifically our x-intercepts. The reason we look at it in factor form so frequently is because of the fact that our factors are really key in determining our x-intercepts, or our roots, right? Our roots here are r, s, and t, and you can write each root as r and 0, s and 0, and t and 0. Okay? So in this case, we know that if we want to find our x-intercepts, or our roots, you let f of x equal 0. And in this case, you can just solve for it very quickly. Okay, so our x-intercepts include 4, 1, and 5. Okay, negative 5, sorry. 4, 1, and negative 5, right? These are values that will make each of these factors 0, and 0 times another factor will give you 0 for the whole thing, right? So your x-intercepts are 4 and 0, 1 and 0, and negative 5 and 0. Okay, so those are our x-intercepts. Now that we have our x-intercepts, you also need to look at the order of each root, right? So if we're looking at the order of each root, right, I'll look at the root, I'll look at the order, I'll look at the behavior, right? You can notice that all of these are orders of 1, right? If you look at the root 4 and 0, the order here is 1, because there's only a power of 1 on the factor, and the behavior will slice through it. Okay, it'll pass through it. The root 1 and 0 here, there's the order of 1, this also slices through that point as well. And the other point, negative 5 and 0, the order of 1, it also slices through. Okay, so that is our order. And you also want to look at your y-intercept. I'll do it out here. Y-intercept, the y-axis, the graph when it hits the y-axis, the y-intercept. You need to let x equal 0, right? Because we know that the y-axis occurs when x is equal to 0. So we're doing f of 0 is equal to negative 0 minus 4 times 0 minus 1 times 0 plus 5, which is negative 4 times negative 1 times 5. And this is going to give us negative 20. So 0 and negative 20 is our y-intercept. Okay, so now we have our y-intercept, we have a series of x-intercepts, right? Now what you can do is determine your sketch really quickly, right? So I'm just going to sketch this guy out, right? Once again, we don't need to create a series of units, right? I just want to plot key points. So I'm going to create a sketch here. I'm going to plot my x-intercepts really quickly. So my x-intercepts, we have 4 and 0. Let's say it's right here. Okay, we have 1 and 0. Let's say it's here. Okay, and we also have negative 5 and 0, which is here. Right, it's not drawn to scale, I know, but try to make it as much to scale as possible. This is 0 and negative 20. Right, we can understand that it should pass through these points, right, and it should start at quadrant 2 and end off in quadrant 4. Okay, so technically what you should see here, I'm just going to erase that line. Whoops, that's not what I wanted to do. Right, technically you should see this thing ending off in this quadrant, and it should start in this quadrant. Okay, and we know that it's going to hit the y-intercept, right? So there's going to be some kind of maximum point here, right? And we should expect 2 turns because this is a turn, right? We can assume that there's a minimum here, but there's going to be a maximum here. Now we need to find our extrema. Now because this is an odd degree function, we can only have local maximum or minimum. Okay, there is no absolute maximum or minimum. The reason for that is because the domain and range for odd functions, x belongs to a set of all real numbers, and y belongs to a set of all real numbers. There's no restriction specifically on the range. This is true for all polynomials, odd and even degree functions, right? However, this will actually vary for even degree functions, right? Because it's odd, there's no restriction. So there is a local minimum at the y-intercept, 0, -20. But there is a maximum point that's located in between, so it's going to be located here. We don't know what this value is, right? This is y, a local maximum. It's going to be in between the two x-intercepts. So you can see that the order of the roots were really useful in generating those intercepts because it passes through all these points, right? Well, we need to figure out what this x value of this turn is, right? Excuse me. So we understand that the x value of the turn here should be the midpoint, right? So it should be basically 1 plus 4 divided by 2, which is 5 over 2, which is like 2.5, right? And if you wanted to figure out the y value of the turn, right, we'll call it y turn, so we'll just keep it consistent. Okay, if you wanted to find the y value of the turn or the y value of the local maximum, what you just do is you just do f of 2.5 and you plug it into your function, right? You get negative 2.5 minus 4, 2.5 minus 1, 2.5 plus, plus 5. Okay, and then if you punch this out in your calculator, you'll get about 16.875. Okay, so this is just there to kind of help us figure out where the point is. All right, so this is 2.5 and 16.875. Okay, so that is our local maximum. We have our local minimum, so our local maximum here is 2.5 and 16.875. So we have our local maximum, and we don't have any absolute maximum minimum. And then we figured out our domain range. So this is our sketch, right? And honestly, this is only possible if you guys look at the degree, the turns, right, the intercepts, the order, right? So that's the idea. That's how we can do curve sketching, by gleaming some of this information of polynomial functions. Let's state the interval of positivity and interval of negativity, as well as interval of increase and decrease, by sketching the function f of x is equal to -1/2 x minus 2 squared times x plus 4. Okay, so let's sketch this function first, and then we can look at when y is positive or negative, or when the function is positive or negative, and when the function is increasing or decreasing. Well, if we want to sketch this function, let's take a look at the leading term here. So the leading term is -1 times x squared, because this term is going to have the highest degree of 2, times x to the power 1, which is basically -1/2 x to the power 3. Okay, so this tells us a here is -1/2, so a is less than 0. So this also tells us that the degree here is 3. So then the total, the maximum number of turns you would expect is 2, so you can have a minimum or a maximum point. And this implies that we have a negative odd degree function. Because we have a negative odd degree function, if we were looking at the end behaviors of the function, right, the end behaviors would be in quadrants 2 and quadrants 4. Okay, so we'd have quadrants 2 and quadrants 4, right? And after we figure that out, the next thing what we want to do here is let's find our intercepts, right? So let's start with our x-intercepts, right? So I'm going to let f of x equals 0, so -1/2 times x minus 2 squared times x plus 4 equals 0. So x can be equal to 2 and -4, right? You can also figure out your y-intercepts here. You know what, I'll just do it in the same color. Y-intercept, I'm going to do f of 0, which is going to give us -1/2, 0 minus 2 squared, 0 plus 4, which is -1/2, -2 squared times 4. So that's 4 times 4 is 16, times -1/2 is -8, right? So f of 0 is -8. Okay, so the point is 0 and -8. Now, after finding our x-intercepts, we also want to figure out the roots and the behavior of the roots, right? So if we want to find the behavior of the roots, right, so our roots here, our x-intercepts here, are 2 and 0, and -4 and 0. We want to look at the order. The order of the 2 and 0 root is a 2. This order is a 1. So the behavior around these roots, right, this is going to pass through 2 and 0, but it's going to, oh shoot, sorry about that. It passes through the -4 and 0, it passes through the negative 4 and 0, but it's going to be concave to the 2 and 0. Does that make sense? So keep that in mind. So after we have our behavior of the roots, we have the intercepts and so forth, we have an idea of how many turns and what the end behaviors are. Let's sketch out this function, okay? So I'm just going to create a general graph here. Actually, you know what? Let's just do it here. Plenty of space here. Okay. So let's create a sketch here. Right, so it's a negative odd degree function. I'm going to plot the roots real quickly. So the roots here, there's going to be a 2 and a negative 4. Right, this is the 0 mark, so this is negative 4 and 0. This is 2 and 0. We have a y-intercept of 0, negative 8. Right, so you know, let's just put that here. I'm not drawing this to scale. Okay, let's say this is 0, negative 8. And we know that the end behaviors here, follow the trace, it's going to be concave to this point, and the end behavior should be in quadrants 2 and 4, right? So it should end off in this quadrant 4, so it should be concave down to 2 and 0. Okay, so let's say it ends off here, and as a result it should go there. It should loop through this. So this is a pretty good curve, I think. Okay, and then it should loop up. Right, once again guys, it's a sketch, right, not too important. However, we need to understand that there should be, right, 2 turns, and we should have a turn there as well as here. So that's good, right? So we do have 2 turns here, that's consistent, right? We don't actually have to find any other maximum and minimum points because the maximum and minimum points are already listed on this graph, right? And because this is an odd degree function, we have a local maximum at 0 and at 2 and 0, sorry about that, and a local minimum. So there's a local maximum at 2 and 0, and there's a local minimum at 0 and negative 8. So keep that in mind. Okay. And you can see there's opposite end behaviors here, positive infinity, negative infinity. Now what we want to do here is we also want to look at intervals of positivity and negativity. Let's take a look at the intervals of positivity. That's basically when f of x is greater than or equal to 0, when it's positive, right? So when it's greater than or equal to 0, we're basically looking at anything above the x-axis, right? And the only point in which that's going to occur is basically when x belongs to negative infinity as well to negative 4. Okay, so this is an interval of positivity when it's positive. For the remainder, right, so the interval of negativity here, when f of x is less than 0, x will basically belong to negative 4 and positive infinity, not inclusive of negative 4. Okay, so that's the interval of positivity, interval of negativity, which you can see out here, right? It's all of this basically, right? So we understand that. Next thing we want to look at is interval of increase, interval of decrease. Okay, let's take a look at the interval of increase. Okay, so interval of increase, you're going to have a positive slope. So if we're looking at a positive slope, you know what, I should do interval of increase in orange, so that way we can kind of... Okay, so this is your interval of increase, and you can notice that you have a positive slope from this point onwards, right? So from 0, x belongs to 0 and 2, in between that, right? So we're just looking at not when the slope is 0. And the other intervals, let's say this is interval of decrease. Okay, so we have an interval of decrease, and that occurs here all the way to 0, right? So x belongs to 0, whoops, a mistake again, negative infinity and 0, as well as 2 to positive infinity, right? So union 2 and positive infinity. So those are the 2 intervals where you see an interval of decrease. So those are our 2 intervals that we wanted to look at: interval of positivity, negativity, and the decrease and increase, right? And it becomes very straightforward once you get all these characteristics down and you sketch the function.